So you made it to task 2. Welcome, everybody. I'm proud of you all that made it to task 2. I'm sure you all got here with no problems at all, probably no errors in your code, and you probably submitted to AutoLab and passed on your first submission.
Man, shut your...
So with that being said, guys, we're going to go over task 2 a little bit, check some things out. We're going to be going over some things that you might need to know if you don't know them already, like linked lists for this task. And we might be going over some strategies on how to do one of the methods that you have to implement later on. So we're just going to go over first some linked list stuff, and then we will go over the task. So, getting started here. What's it all about? Like I said earlier, we are going to be using a lot of linked lists, and they're going to be used for many different things, especially in this assignment. And one of those things are refactoring our level logic. Currently, we're able to go to 3 different levels you've seen if you've completed task 1, which obviously you all have. So after you get to like this blue house here thing, you go to another level where there's enemies surrounding another one of those blue houses, and then you go to a level that's win. So currently the way that system's made is kind of sloppy and hard-coded, and we're going to make that better using linked lists. But then we are also going to use linked lists for pathfinding. As you can see with this red arrow here, enemies will now chase the player, which is going to make our game a lot more interesting. And there's some different ways you can implement this, but I'm going to talk about one that will be very useful for the future. Although you don't need to do it that way for this task, but I'll get more on that later. And yeah, enemy stuff. So enemies will use the path generated from your pathfinding that you also implement. And so they're not just going to be standing anymore, which is great. Okay, so I just recorded a whole part, and my camera was blocking this very essential piece of information, so I'm going to do that again. So, about linked lists. I pulled this image directly from the lecture slides. So, you all should have seen this by now, of course, because you're all going to lecture. And, yeah, so this is a linked list. And Google defines linked lists as such. A linked list is a data structure that stores data in a chain of nodes, where each node points to the next, which is exactly true. So here in this example, we have a variable called first, and first points to a linked list node. And here we could tell that the value is an integer, which in our first node, the value is 3. And as Google says, we store data in here, which is the value. So 3 is an int, which is the value of this node, and all linked list nodes store 2 things: the value and a pointer to the next node. Again, you all should know this. I'm just going to go over it real quick. So as we see here, this node, its value is 3. Its next pointer is to another node, which is this node right here, and its value is 2. And it also has a next value, which is a reference to another linked list node of type integer. So we check that, and that also is pointing to another node here. And we see this node, its value is 1, but its next is null, which is totally fine. Whenever we see a node that's next is null, we say that this node is the last node in the list. There's no node after that because there's no next. And so yeah, so first, these are all nodes that have a next value, and this one is null, which is totally fine. And in case you guys were confused sometimes, because I know we use a different class in your project. So here we have a linked list node of type integer, and it is called first. I made this code just like the example here. It's equal to a new linked list node with the value starting at 3 and the next pointer starting at null. And what I also did is I used the methods that are available to you in the task. And we're going to take a look at the linked list class for the project in a second. But basically, both of these appends here do different things, but they're valid. So here we say first.append 2. So we're directly giving it a value. Remember, it's a linked list node of type integer. So append has 2 overloaded append methods. So here we see that we could just give it a straight up value 2 here. And here we make a whole new linked list node and give it to it. I need another parentheses here, I know. But, so this is totally fine. You're allowed to do it both ways in your task. So if we append 2, it's going to create the next node and add it on to the end of this linked list. So ignoring this node here, after this line of code with the append 2, we would get these 2 nodes. And the second one would point to null after this line. Because the append method will create a new node for you if you just give it a value. And this append is totally valid as well, but we already make the linked list node, and we append a new linked list node into the value to 1 and next to null. And then we have a linked list that looks just like this according to this code. So now we're going to take a look at the linked list class just so I can show you the parallels right there. Okay, so this is the linked list class. And as we could see, there are 2 appends. And as we saw on the slides, this one just takes a value, and it says its type is T, which you guys might have not learned much about generic types yet, but basically that just says that like whatever we made our linked list out of, so if it was integer like in the slides that I just showed, then this T would be integer, or whatever it is. You make linked list nodes of a bunch of different things in this project. So this one just takes a value, and as you can see, you can read this code yourself. It's in your project. All of you guys have it. Don't change this code though. Do not touch it. We're just looking at it. So we see that this append here makes a new linked list node for us, given the value, which is great, and it adds it onto the end of the list. And otherwise, you could use this append, which you give a linked list node, and as you can see, it adds it to the end of the list as well. But you might also be seeing that like this method calls itself. Which is interesting and a thing that we're going to look at, and I'm going to bring up again later for something. But again, we're not there yet. I'll get there in a little bit. But so yeah, let's head on to the task and take a look at the document. Okay, so we're in the task 2 doc now. For some of you, this is probably very refreshing to see after task 1. We'll see how long that lasts. Anyways, so remember, this video isn't like a replacement for you guys reading the doc. Definitely read it very well through. And read it very clearly. And don't skip any lines, because like even up here, you might see like project structure. Oh, okay, let's read the specification. But no, read it, because you will notice some things that are very important. First of all, you see everything that you're going to be using in this task. Like sample top-down game is going to be a class that you write a lot of code in. Same thing with enemy, and then you read, oh, pathfinding, cool. But then you're going to see like, oh, I have to make a package, which it does specify below, but still, if you want to be more clear, then read it here. And you see that you're going to be using a lot of linked lists. But so yeah, pathfinding, you're going to create that class yourself, and you're going to make a package for it, which I will show you where that's going to be. app.gameengine.model.ai. This is the package that you have to make. So if you go to, this is your directory here, source, main, Java, app, game engine, model. So you're going to see app, you're going to see game engine, open up model. Right here is where you need to make your own package. So you'd right click on this folder, click on new, and where is it? Right here. So you see package here, click on that, and you're naming it AI, because pathfinding has to deal with AI. So yeah, that's something you have to make, and then yeah, you should just read the rest of this. You're going to be using linked lists. You can't modify its code, especially for testing. So anyways, let's get into this a little bit. So first thing that you guys are going to be messing around with will be sample top-down game. Now, as I was describing earlier, currently, and as the doc says, the game handles levels in kind of like a poorly implemented, hard-coded way, as this says right here. So we're basically going to override this functionality by first making a whole bunch of getters, setters, and some handy methods to manipulate our levels. So some important things to note here is you are going to be making a instance variable, which is a linked list node of type level. So you see that right here, that you will make an instance variable of type linked list node of levels, which if we were to look at those slides or just a linked list, we see that this linked list node of type, this is what of type means whenever you see these carets. Here it's of type T. Yeah, so right here, we see in the slides we have a linked list node of type integer. We're going to make a linked list node of type level, and that's going to be an instance variable. So, and once we make this instance variable, we are going to be making some methods for it, which are a get level list, which will return it, set level list, which will set it, and stuff like add level. So when you call add level, you would expect to add the level that's the parameter of this method to be added to your linked list. So it's important here to remember, but when someone calls add level and you have add level, you have an instance variable of linked list. Now I don't see anywhere here in this task that says that the constructor is supposed to initialize it. The list should initially be empty. Please use the provided. Yeah, so strange. This is something to keep in mind when implementing add level. If you add level but your list doesn't exist yet, what's going to happen? I don't know. That's up for your testing and your thinking, most importantly. So keep that in mind. Also, remove level by name. So this is a method that takes a string and returns void. And you're going to basically search through your linked list of levels and find a level and remove it if the name is equal to the one that the parameter gives. And if you remember, to remove something from a linked list, you simply have to change the next pointer or reference to the node after your current node's next. Let me explain this in a visual. Okay, so this visual represents a linked list. And let's say this is our linked list of levels. It's not, because the value here are integers and not levels. But let's just say it's a linked list. And I want to remove anything from a linked list. In the case that these are levels, it's going to be an object that has methods available to you that will help you get that level's name. So in the case that we want to remove a level by name, we're going to have to check the name of the level while we're traversing this list. And if it's the level that we want to remove, meaning that it has an equal name to the one that was passed into the parameter, then we want to remove it. So let's say here these levels are, or these nodes are named, these are strings, okay? And this is the level's name, which when these are stored, they're not going to be directly strings. They're going to be objects of type, like this is a level. This is going to be true for all these ones. And you will have to call like .getName on those ones. So don't be too confused by this. Anyways, if this is our linked list of levels and I want to remove the level named 9, for some reason it's named 9, I would start at the beginning of my list and I want to check for the level that is named 9. Now, if I'm traversing and I'm hopping through like, oh, this one named 9, nope, let's hop here, this one named 9, oh, it is, remove it. Well, how am I supposed to remove it now when I'm like at that node? Because how you remove something in a linked list is by changing the next pointer of the node before the one that you want to remove and making it to the pointer of what your old next was pointing to, which was in this case 87. So we would remove this from 9 and set it to the next value of what our next was. So our next was this. Get next would previously return us this node. And this node's next points to 87. Now when we want to remove this node, we need to get the value of the next node from the one that we want to remove, which in this case is 87. And we want to set it to our current node. And then so now this node has nothing pointing to it, so it'll get garbage collected, it's gone. And now we have a linked list that's pointing from here to here. And we remove the level named 9. So it's like kind of a sloppy implementation, not getting into the weeds with it, but you might think here, like, how would you remove a node, especially if, you can't remove it if you're just traversing through the list and you reach that node. You have to do some thinking there and think, how am I supposed to get, my next, and see if that's the one, think about it there. Okay, and the last thing we have to do in sample top-down game is modify a method. And we are modifying the method called advanced level, which is right here. It's you go to, you're going to find sample top-down game, which you're already going to be in because you were already working in it. I don't have any of the implementation that you were supposed to do, of course. But this is what you were given from like the last task. It's what you use to actually play the game and advance the level right now. But as we can see, it's a hard-coded implementation. We're like using if-else, and if we have like 800 levels in this game, we don't want to type 800 like if-else statements. So it's sloppy right now, and we want to change that like quick. And we are going to do that with our linked list. I recommend when implementing this, make sure you read very carefully for this one, because in the doc explicitly states like use get current level to access the current level, which is a method available to you. Like if I were to just type get current level, we'd get a level. So level current equals get current level, and we'd store it in a variable if we wanted it. This isn't doing anything. Don't use this code, of course. But yeah, get current level is if you're like, oh, where is it? It's not in here. It's because it's in a class that you inherit from, which is game. So yeah, that has this. Anyways, you're gonna implement this, and I'm not gonna say too much about it because this will test that about linked lists. But when it's done, you're gonna notice that if you were to comment this out and you were to run into one of those blue houses, nothing happens. Like you don't change level. If you comment this out and implement it with your linked list thing, your game should work exactly as it used to work at this point. But now it's way better because you refactored a lot of stuff about how level loading works, which is great. So a great way to tell if your game is working is by commenting this out, implementing what you used to, or implementing loading a level with advancing level with your new implementation with linked lists, and if it works the same way, then you're good, and you get to the win stage after you beat the game. So that is all I have to say about sample top-down game. Now we move on to pathfinding. I have been saying that I want to talk about a certain way to implement pathfinding that is going to be useful to you guys, especially for future tasks, especially. If you follow my advice, you will have an easier time in the future, but it's not required to implement in the way that I will demonstrate. So I could read through this whole thing here, but I'm going to let you guys do that. But a few things I will note and point out is that you're going to create a pathfinding class in the AI thing that we made earlier, which is in model AI. So yeah, we're going to make a new class here, new Java class, name it pathfinding. I'll just do that real quick. Pathfinding. And I'm not going to stub out, or I'm not going to create the method for you because at this point I think you guys should actually be able to do it just fine, and you should get used to doing it. So you're going to write a static method called findPath that takes in two vector2d objects as parameters and returns a linked list node of vector2ds of type vector2d. So, read this very carefully. And now, though, I'm going to get into an implementation tactic. Actually, I changed my mind. Before I show you the implementation tactic, I'm just going to go over basically what this method is expecting of you. So there's a lot of stuff on your screen right now. Chillax. So this method, findPath, we give it two parameters, a start and an end. And I have those highlighted right here. Start and end. These are vector2ds. Now, from any start, we want to return a linked list node of type vector2d, which is a path from the start to the end. Meaning the first vector2d in the list should be the start, which it doesn't have to be the same reference that's given to you, but it does have to be the same x and y as start. The first should be start, and the last one should be end. Which, that part is easy, we could get the start and the end, but everything in between is the harder part. Meaning that, like, if we have a start of 0, 0 and an end of 2, 3, we expect to be returned a linked list of all of the nodes to get there back, which in this case it would be 0, 0, 1, 0, 2, 0, 2, 1, 2, 2, and then 2, 3. That's a path as displayed here from the start to the end. Now, something that I have to point out is this would also have been a valid path. Going down the y direction first and then moving over the x's would have also been a valid path, because you have start and you get to end, and these paths are the same length. They're both the shortest path that you could use to get there. So totally fine. If I were to like go down and went like 0, 1 and went all the y direction first, that would have been fine too. Just want to make sure I point that out. But an attribute about these nodes and this path is that every node, so let's take a look at this node right here first. No node adjacent to this node can have a difference of more than 1 in the x or y direction. Meaning that from this node, let's see, on the list it's this one right here, so I'm going to highlight it. The only nodes that can be next to this one are nodes that are either 1 down, 1 right, 1 up, or 1 left. So as we can see here, this is perfectly valid. The node to the left of this one, or the node before this one, is differs only by 1, because we can see 1 and 2 differ by 1. And in fact, we want to take into account the whole vector here. So if we just subtract these vectors, if we subtract any 2 adjacent vectors in this path, we will find at most either the x is going to be 1 or -1, or the y is going to be 1 or -1. So like if I subtract 2, 1 from, or if I subtract 2, 0 from 2, 1, I would get 0, 1. So, and you could do that with any 2 adjacent vectors in the list, and you'll get that difference, or a difference of at most 1. So this is important because we want to hop over only one cell at a time in this path. And also, something that the task specifies is you might be given a start with like, that could be like something with a decimal. So like, say we were given like 7.976 whatever, comma like 8.2. It's our job to truncate this decimal. We don't really care about it. We want to say, okay, if you're standing like, even if you're standing so close to 8 that like you're basically at 8, no, we get rid of everything that's not that's after the decimal point. We want to say, okay, if you give us the sloppy number, we're going to set you right at 7 to start, and then we're going to start pathfinding. And same thing for end. If you're given a weird end with some like decimal points, we don't really care about the decimals. We just want the whole numbers. And so this list would not be valid if any of these, if any node that's adjacent to the node that you're currently at does not differ by 1, or if any node in the list had a value in its vector that was not a whole number. That would be considered an invalid node. So this list right here is a good example of a valid list from the start of 0, 0 to the end of 2, 3. Keep in mind that your start and end can be any vectors, and it should reach them accordingly. So that's what this method's expecting. Now, I'm going to get into an implementation tactic. Recursion. How I love recursion. So you guys have seen it before, and I actually pulled this image from your lecture slides. Here we see an example of recursion where we call append over and over again until our next is null. So something to point out about any recursive method is it has a base case where it stops being recursive at a certain point. In this method, append, we are saying that recursion is going to stop if this dot next equals null. And we know that because if this dot next is not null, we go into this else and we make our recursive call. So this is the dangerous thing. This is like what's going to keep something happening and making a new stack frame like forever and ever and ever until we reach the base case that says, hey, don't do that anymore. So This is something to remember about recursive methods, and you might be thinking, why are recursive methods useful in what we're trying to implement? Well, they happen to be extremely useful. So we see in this example, we're given a start and an end, meaning we have two pieces of information, and we want to return back a list of every single node up until the end from the start. So this makes a great case for recursion. And that's because we see we're going to have to make a repetitive call over and over and over again, which you might be immediately thinking like while loop, for loop, something that's not recursion. And you know what? You could probably do it that way, and it would probably work for this task. But I'm telling you right now, you're going to have to do recursion in the future, and if you want some early practice to save you time for a harder task in the future, then I would try to implement recursion in this task. And so most most methods that are recursive have some sort of helper method before it to help call it. So if I'm saying like, hey, you might want to try recursion for this method, a lot of you will probably be completely clueless on where to even start. So I'm just going to give a slight example. Everything I say beyond this point is a recommendation. You guys, most of you are probably going to do this with loops, but this is a recommendation and some advice, and take what you want out of this and think about it yourself. So our given information is that we have a start and an end point. And what we need for our recursive calls is a vector denoting the current position, a vector marking the end position, and a linked list to append to. So basically our strategy is going to be, okay, we're going to start at a certain point, which is going to be 0, 0 in this case. And we are going to say, okay, the start, doesn't matter anymore. We're just considering that 0, 0 is our current point. If 0, 0 is our current point and we have our end at 2, 3, we're going to decide, should I move closer in the X or the Y to get closer to 2, 3? That's up to your choice. But I'm going to choose X because, that's this example that we already have. So we're going to say, okay, first of all, if we're going to check if this is equal to the end. Because if we're already at the end, we want to quit recursion. So if we're not already at the end, then we need to say, okay, we want to get a little bit closer. So I'm going to increment by 1 in the X because 1 is closer to 2 than 0. And we can only move 1 at a time. So I'm going to do that. I'm going to create a new vector 2D. I'm going to append it to the list. So our list is now going to be looking like this. And then I'm going to recursively call again on our new current position, which is 1, 0. It's tough to describe in just words on how to do this. I have a little bit of pseudocode here for us to analyze. So our find path is going to be called with a start and an end. And we already know we need to make a linked list and find a path. So making a new start node is pretty obvious. At least we need to make a bunch of linked list nodes of vector 2Ds. So we're going to create our starting node because that's something that we're going to need no matter what. And so a common, like I said before, technique with recursion is to use helper methods. So in this case, we would call a helper method, which I have in pseudocode defined here, that takes a parameter of vector 2D current, end, and head. Because like I said before, we're going to take our current vector that we're at and move it just slightly closer to end every time this method's called. The goal of this method is to move current slightly closer to end, and exactly 1 unit in the X or Y closer. So the first thing that this method should do is check, should I even keep going in this recursion? Like if I'm current and I'm equal to end already, then I don't need to do anything. We could end there. So in this scenario, we're saying that imagine current is 0 right now, 0, 0, and end is 2, 3. So in this case, to our human heads, we will say yes, we should keep going. So we should make a computation, right? And there's some logic that you guys have to implement here to decide, where you should actually go. But for just an example, we'll say that like we compute that our next place that we should be is 1, 0. That should be our next point in the path because that's a little bit closer to 2, 3. So We'll say this is our new current point right now. And we're going to use this point that we just made and append it to the list. And you might be thinking, like, how do I append it to the list? Well, conveniently, every time we call find path helper, we pass through the head of the start node that we made earlier. So since we have head, we could just call head.append and append the new node that we made. And that is going to give us this structure right here. Because appending this to whatever the head was, which is this, will give us this. So we append it, and then we call recursively find path helper, but instead with our new current, which is 10. And this whole process will repeat again. Everything we just did will happen again, except now our current is 10. Our end stays the same. We passed in the same one again. So 2, 3, and our head is the same thing as we had before. We're passing the same head and end over and over again. The only thing that's going to change in this recursive helper is current. So we then ask ourselves the same question. Should I keep going? Well, current is 10. Is that equal to 2, 3, end? No, we're not done. We got to keep going. So again, we're going to compute. We're going to say with our human brains that 10 to get closer to 2, 3, we're going to make it 2, 0. Again, you guys have to implement how you actually get there to 2, 0, how to make that new vector. You guys got to do that yourself. But I'm at 2, 0. And I'm going to say, great, I have my next point, append it to the list. So when I append it to the list, I add on to the last node here, which is all done for you in append. And now we're going to have this structure here. Great. As you can see, there's a pattern here. We're starting to make a path. And so we append it to the list. And now we say, okay, find path helper, go again. And this time, call with our new current, which is 2, 0. And I will do this one more time. So again, when we call it with our new current, that's the only thing that's changing. Now, in our next call, current is 2, 0. And end is the same. It's 2, 3. But now, we look again. Should I keep going? This time it's a little bit different because, oh, our x's are equal. Current.getX is equal to end.getX. So, yeah, we're good in that end, but are we good in the y's? No. 0 is not equal to 3. So, we're not done. We should keep going. And now we compute. With our human brains, we could say the next closest point is no longer increasing in the x. It is now from 2, 0, it should be 2, 1. Because remember, we can only move one unit at a time. So we say it should be 2, 1. Great, we have our new current. And with this, we want to append to the list. Again, as we've shown with all the other nodes, when appending to the list, we now have this. We do this one at a time, and we get closer and closer. And I said I'm choosing to go x's first in this example. So, you know, we're increasing all the way up until where we're supposed to be, and then we're going y's. But again, like I said before, you could do it the other way here. But I'm going x's. So we have 2, 1. We computed it and we appended it already. And then we call it again. New current, new current, new current. Append find path helper. And this is going to go, this recursive, you see a pattern now. This will go all the way until current is equal to 2, 3. Because remember, our end is equal to 2, 3. So, in this sense, we've computed it. And in this recursive call, we ask ourselves, do I keep going? Well, current is equal to end. So I'm like, oh, wait, we're there. We're good. So I don't need to keep going. I don't need to return anything. This method will have a void return type. I'm not returning anything. I'm just adding on the head. I'm just saying that I'm going to find something from current that's a little bit closer to end and then append it to head. That's what our recursion is doing. And after this whole thing is done, we will have this whole entire list. And yes, 2, 3 will be included because when we got to this point in our recursion, we said compute the next one, which was 2, 3, append it, and then call find path helper on 2, 3, which is how we even got here in the first place. So yes, all of these will be our complete path, and this is a valid path, and it's done with recursion. I get that this is pretty like abstract and probably weird and different than loops, but if you guys want to get a head start and be better prepared for future tasks, I recommend implementing recursion. So with that being said, I'm going to get into the last bits of the task and let you guys on your way. The last thing you guys have to implement is in the enemy class. You're going to have to implement set path, get path, which, compared to the find path thing, it's a lot lighter. So you guys can read these and probably do those by now. You've done a lot of getters and setters at this point. You guys should feel more confident in that. But the interesting thing here is update. Update takes a double and a level and returns void. It's called every single frame of the game. And basically, this method is pretty simple. You just have to check. You're only doing one of three things ever in this method. You're either computing a path, advancing to the next node in the path, or traveling along a path. So the hard part was computing find path. So you're going to compute that path, and then you're basically saying like, okay, once I have a path, I want to say, okay, compute where I should be next if I'm at, if I'm already at like a node, I want to say, okay, give me the next one. That's a stage. These are states that you could be in, or travel along a path, which is saying like, okay, I'm not at the node that I want to be at yet, so change my velocity and go towards the node. Which I'm not going to get into any specific implementation here because I believe you guys should be able to do most of this, especially after implementing find path. It shouldn't be that hard. The hardest part here is probably going to be computing the velocity. So if you guys have questions about that, you might want to stop at office hours because again, more mathy vector stuff. But it's not too bad. Again, the bulk of this was find path. And after this, you have your testing utilities and your testing requirements, which is just on your pathfinding. All this stuff with sample top-down game, you're not actually testing in this. If you want to write your own test for it, you could try, and that would be great practice anyways, but you're not going to be graded on that in the autograder. So you're making a testing utility that's validate path. And remember what we said earlier about a valid path, where the only valid paths are paths where no vector in this path has a non-whole number. So if any single one of these had a double, like let's say just randomly in the middle, we had this was actually 1.02. It barely looks like that, but that's 1.02. This would now be a completely invalid path. Wrong. This path is wrong. I hate it. It's just a wrong path. Also, it would be an invalid path if any of these nodes were more than one apart from the previous. Or any adjacent. So remember how we said if this was I don't know, let's say this was 8 and this was 10. First of all, it's not a correct path. And second of all, they're way more than one apart. This and this are this is a one here, 7 apart in terms of number units. So yeah, those things are what indicate a valid and invalid path. Make sure that every vector has whole numbers, and make sure that no adjacent nodes are more than one off. And that's basically what you write this testing utility about. And literally, if you make this testing utility, testing find path and your testing requirements is crazy easy. The hard part is validate path, but it's really not that hard. Go through your entire path, make sure it's right in every single node. And yeah, that's pretty much it, guys. So good luck with this task, especially the recursion, because it's going to be hard if it's your first time doing it. It's tough conceptually, and it's different to implement logically. So if you do want to do it, please do try. And if you need help, come to my office hours, or other TAs I'm sure will help you with recursion. But if you want to talk specifically to me about it, I'm down to totally help you implement it because it will be useful to you later on. I know it's kind of tough for me to show a great way over this little video that I made here and drawing in Paint. So yeah, if you have more questions, definitely stop by office hours or any of our office hours. And good luck on task 2, guys. See ya at task 3.